This is week 6 of upper thermodynamics course. So this is continuation to the previous Brayton cycle which we saw. So previous week we got an introduction of the Brayton cycle. So we started with the Rankine cycle and we differentiated Rankine cycle in Brayton cycle. So Rankine cycle is a wave power cycle. So it operates in a two-phase region. But Brayton cycle is a gas powered cycle, so you have the working fluid is in a gaseous form. So that's the main difference between the Brayton cycle. But the process is all four processes are all same. So we have two isentropic processes and two constant pressure processes. So those are the processes for an Rankine cycle as well as for an Brayton cycle. And also we looked at how to improve the efficiency of this Rankine cycle in the previous case, and in the Brayton cycle also we saw a normal cycle, Brayton cycle, an idle cycle, and with your efficiency of turbine and compressor, and how this efficiency influences your efficiency of this Brayton cycle, how it is sensitive to your turbine and compressor efficiencies. With that, today's questions are somewhat related to the Brayton cycle, but we'll have some additional processes where we have regenerators and so on. Even in Brayton cycle, you may have reheating and intercooling kind of process. We will see that also. First, we'll start with a process having a regenerator. So what is a regenerator is you heat the fluid with the exhaust which you are getting. That's the main idea of a regenerator, and that is the cycle which is shown here. Hello? हाँ बोलिए. नहीं ये requirement नहीं है. Thanks. So this is how the process looks. So your conventional Brayton cycle or the gas powered cycle will have compressor. Initially you are compressing from 1 to 2, and then it is sent to an heat addition process, or normally what you do is you have some fuel which you combust to increase the to provide energy or to do a heat addition. So that increases your energy, and that is expanded in a turbine and is sent out. So you see in the diagram, your inlet is at 1 to the compressor, and then you're compressing it to 2A, and then you heat it to 3 for suppose without any regenerator. If you use fully add heat and send it to 3, the temperature is around 1300, and then if you expand it in the turbine, it will come to 4A. But if you compare 4A and 1, 4A is at a higher temperature compared to the inlet temperature of air. So this normally this is an open cycle, so you leave this exhaust gas at 4A to the atmosphere. So you are losing that much amount of energy, so you are wasting that much amount of energy, so you are not fully utilizing the heat which you have provided. So a better way to do is to heat the incoming fluid to the combustion chamber. So a part of the heat is provided by this exhaust gas, and the remaining heat is what is provided in the combustion chamber. So effectively what this does is you have reduced the amount of heat which is given, but you are getting the same amount of work. So this will technically increase your COP. So that's what is shown here. So initially you have a compressor, you're compressing it, and then it goes to a regenerator where it gets heated from 2 to 5 by the exhaust gas which is coming out of the turbine, and then this gas air is heated in the combustion chamber, and then it goes to the turbine, and then it goes out and then goes into the regenerator. So this is how the process looks for a regenerator cycle. So what is asked is to determine the thermal efficiency of this gas turbine described in the problem which we saw in the previous week, but with a regenerator. So this is how it looks. The maximum temperature is 1300 and the minimum temperature is 30, and the effectiveness of heat exchanger is given as 80%, and you have the turbine and compressor efficiency is given. So with that we'll see how much difference it's making. So the first is the efficiency of the regenerator. So actual is H5 minus H2A divided by the maximum which can be provided by the regenerator. So regenerator fully, if you want to heat, so then the maximum heat which it can provide is H4A minus H2A. That's the maximum enthalpy at which there is fluid is coming in, minus the hot side one. So that's the maximum Q max which it can be given, minus the what is provided by the regenerator is 5 minus 2A. So H5 minus H2A divided by H4A minus H2A. So your effectiveness is given as 80%, so it is 0.8. So so the enthalpies are, so H5 minus 605.39 divided by 880.36 minus 605.39. So this gives me H5 as 825.37 kilojoule per kg. So now your heat input is H3 minus H5 instead of H3 minus H2A. So that is your heat input. So it has gone down by H5 minus H2A. So now the heat input is 570.60 kilojoule per kg. So this says that the heat input has gone down by 220 kilojoule per kg. So or else this heat has to be provided. So now we have saved this much amount of heat addition. So with this the work output will not change, so that remains the same. The only change is in the heat addition, so that has reduced because of the regenerator. So with that the thermal efficiency now is, the net work will remain same, which is 210.41 kilojoule per kg, and the heat input is 570.6. So that gives me the thermal efficiency to be 36.9%. So in the previous case, when regenerator was not used, in that case the thermal efficiency was 26.6%, but if you see using a regenerator, it has increased the thermal efficiency from 26.6% to 36.9%. So there's a 10% increase in the thermal efficiency because of the regenerator. So but this also comes in a cost that it has to be invested in the regenerator. So the increase is a capital cost. That's the difference between the both, but you get an increase in efficiency. Next is, we have an ideal gas turbine cycle with 2 stages of compression and 2 stages of expansion, and it has an overall pressure ratio of 8. Air enters each stage of the compressor at 300 Kelvin and each stages of the turbine at 1300 Kelvin. So determine the back work ratio and the thermal efficiency of this gas turbine cycle, assuming no regenerators and an ideal regenerator with 100% effectiveness is used. So this is a combination of the previous problems. So what we do is, now instead of compressing it in a single stage, because the pressure ratio is 8, we are compressing it in 2 stages. So you are compressing from 1 to 2. Then what you do is you put an heat exchanger to cool it back to 300 Kelvin, that is the ambient, and then compress it again to 4. So what will this do is, you will bring down the net work done for the compressor, and then what we do is the heat addition here, and then we expand it in the turbine, and this expansion is also again happening in 2 stages. If you see, from 6 to 7, and then we are reheating again to 8, and then expanding it again to 9. So that's the expansion process. So we are getting work done in 2 parts. So for this we need to find out the back work ratio, and also the thermal efficiency when there is no regenerator used and when there is a regenerator being used. So in this case, regenerator, so it says that it utilizes fully, that's an 100% effectiveness. So what that means is, you get same from, if the exhaust is coming in from the turbine at 9, so it will come to till the temperature where the compressor is exiting. So you get that much amount of heat can be added. So with that, we'll see how to solve this problem. So here for 2-stage compression and expansion, so the work input is minimized and the work output is maximized when both the stages of the compressor and the turbine have the same pressure ratio. So that this can be proven that you write it work done, net work input to the compressor in 2 stages in terms of pressures, and then you differentiate with respect to the intermediate pressure and make it 0, and try to solve for that pressure. So that we'll find out that it will be square root of the final and the initial pressures. So that will be the intermediate pressure. So that's what this basically says. So if you see P2 and 3 are same, so if you cross multiply, we'll get P2 P3, which is P2 square equals P2 equals root of P4 into P1. So that's what we get from differentiating the work expression for the intermediate pressure, and that basically comes out to be that pressure ratio is equal between the stages. So with that said, the problem says that the pressure ratio is 8. So for each of the stages it will be root of 8, so it comes out to be 2.83. and same for the expansion. So air enters each stage of the compressor at the same temperature, and each stage of the ice has the same isentropic efficiency. So this is an ideal case, so it's all 100% efficient. So at each of the compressor inlet and compressor exit, your enthalpies are same, and same for the turbine. So when there is no regenerator present, in that case T1 is 300 Kelvin and enthalpy corresponding to that is 300.19 kilojoule per kg. So this can also be written in terms of assuming an ideal gas, Cp into T, assuming your temperature is enthalpy is 0 at T equals 0, and then for T2 your enthalpy is 404.31 kilojoule per kg, and T6 is 1300 Kelvin, so enthalpy is 1395.97 kilojoule per kg, and similarly for T7 your enthalpy is 1053.33 kilojoule per kg. So when you substitute the enthalpy values, your compressor in is 2 times of a single stage compression, because both the compressor now identical, they are operating between same pressure ratios and inlet temperature, so it will require the same amount of work. So 2 into compressor in single stage, so it will be 2 into H2 minus H1 gives me 208.24 kilojoule per kg. So this is the net compressor work which has to be provided, and similarly turbine work which is generated is 2 times the work which is generated in a single turbine. So 2 into H6 minus H7, so this gives me 685.28 kilojoule per kg. So with this, the net work which is generated in the Brayton cycle is 477.04 kilojoule per kg. The heat addition is now in two stages. If you see, one is the initial heat addition, and then what is done for reheating back in the intermediate stage between the two stages of turbine. So H6 minus H4 plus H8 minus H7. So substituting the enthalpy values, you get 1334.3 kilojoule per kg. So the back work ratio now is compressor in divided by turbine out. So compressor work is 208.24 and 685.28 gives me 0.304, which says that 30% of the work generated is getting utilized in the compressor. And the thermal efficiency now comes out to be 477 by 1334, which is 35.8%. So if you see a comparison of the results with those obtained in the previous problem. So when we assumed it to be an ideal case, when the compression expansion process were 100% efficient, so it's truly isentropic, then in that case it says that the multi-stage compression with intercooling and reheating has dropped down the back work ratio from 40% to 30%, but it also has reduced the thermal efficiency from 42.6% to 35.8%. So doing this has reduced both thermal efficiency but also and the back work ratio. So the thermal efficiency has reduced because a large part of heat addition has to be provided. So because of that, your thermal efficiency has reduced, and the back work ratio is reduced because using intercooling and reheating has increased and decreased your work. So therefore intercooling and reheating are not recommended in gas turbine power plant unless they are accompanied by regeneration. So we'll see what regeneration does. So if we do an idle regenerator, which is 100% effectiveness, then the net work output and the back work ratio of an ideal gas turbine cycle are your back work ratio will still be 30.4%. So and the heat addition is the primary heat plus the reheat. So it will be same if you see in the problem. So it will be 6 minus 5 and 8 minus 7. So it will be 2 times of H6 minus H5, which is 685.28 kilojoule per kg. And the thermal efficiency now, if you see, it has increased to 69.6%. It's a very large increase compared to the previous problem. The previous case, your efficiency was 35.8%, but it has increased now for the same back work ratio. It has increased to 69.6%. So using a intercooler and regenerator, intercooler and reheat only makes sense when it is accompanied by a regenerator. So even if the regenerator is not fully efficient, so in that case it will drop a little, but even the efficiency will still be higher compared to the previous cases. So if you see, the thermal efficiency has almost doubled compared to when it was regenerator was not used. So but the assumption here is everything is 100% ideal. So having inefficiencies, this will drop. So it can come to 50 or less than 50%. So as the number of compression and expansion stages increase, the cycle will approach the Ericsson cycle, and which will have the same efficiency as Carnot efficiency. So if you compare with that, you will get 76.9% for the Carnot efficiency. But here it says multiple expansion, but having multiple expansion will again have problems once its capital cost will go down, but then each pressure ratio between each of the compressor and expansion will also come down. So the cycle may be ideal, but having more than 2 stages will not make practical sense. So this moving towards Carnot efficiency 76.9, it requires multiple stages, so it may not make practical sense. But to just show a comparison, you get 77, close to 77% efficient in ideal cycle. So moving on to next problem. An industrial plant is equipped with a regenerative gas turbine cycle as shown in figure. The air inlet condition at the compressor are 101.325 kilopascal and 27 degrees Celsius. The compressor pressurizes air to 10 times the inlet pressure, so your pressure ratio is 10. In addition, the maximum air temperature in the gas turbine is measured as 790 degrees Celsius. So also a temperature difference of 10 degrees Celsius is measured between the cold air stream leaving the regenerator and the hot air stream entering the regenerator. So the net mechanical power output is 106 kilowatt and the heat input source temperature is 2500 Kelvin. So they have already given how much power is generated and the heat source temperature is given. Also the compressor and turbine operate with isentropic efficiencies of 87% and 85%. We need to determine the heat rejection and addition rate for both the actual and ideal cycles. Determine the entropy generation rate in the combustion chamber. Find the exergy destruction rate in the combustion chamber. Determine the energy and exergy efficiencies of the cycle. So I'll first break it down what is given. So we know the inlet to the compressor, the temperature and pressure is given, then the pressure ratio is given as 10 and the maximum temperature is given. So that will happen after the combustion chamber. So your turbine inlet temperature, so that is given 790 degrees Celsius, and they are saying that the temperature difference, so I'll just go back to the, so this regenerator, if you see the exhaust cold out temperature and the inlet from the compressor, that temperature difference is given as 10 degrees Celsius. So your 2 to 6, so that is given as 10 degrees Celsius difference. And the output power is given and the source temperature is given. So we'll see how to solve this. So this is how the cycle looks. Okay, so I already have it here. So this 2 to 6 is given as 10 degrees Celsius difference, and then your inlet temperature is known and the pressure ratio, so 1, ideally it should go to 2s, but we have inefficiency here. So the compressor is 87% efficient and turbine is 85%, so you will go to 2 and then it will get heated in the regenerator to state 3, and so indirectly by giving the temperature difference, what they have said is the regenerator is not 100% efficient, so that's what they mean. So it goes to 3, it will not go to 5 or 5, so it will go to 3, so it will be lower than the temperature at 5, and then again there is heat addition to 4, and then you are expanding, it will go to 5 instead of 5s. 5s is ideal one, and then you are passing through the regenerator to the exhaust. So the maximum temperature is at 4, which is your turbine inlet. So to first we'll find out the ideal temperature when you are doing an isentropic compression. So it will have T2S. So T2S is T1 into pressure ratio raised to power gamma minus 1 by gamma. So this is for an adiabatic process. So T1 is 300 Kelvin, which is the inlet to the compressor, and your pressure ratio is given as 10, and gamma for air is 1.4, you assuming. So you will get your T2S is 579.2 Kelvin. So now for an actual compressor exit, because it is not 100% efficient, so efficiency is your ideal by actual for a compressor. So ideal is assuming it's an ideal gas, your Cp is constant, so Cp cancels out, so you get T2S minus T1 by T2 by T1. So rearranging, this is what you get. T2 actual is T1 plus T2S minus T1 by your compressor efficiency. So this gives you T1 is 300 Kelvin and T2S we have found out, and the compressor efficiency is 87% efficient, so it is 0.87. So arranging, you get T2A as 620.9 Kelvin. So similarly we do it for the your turbine exit. So the same way, T5S is T4 by 1 by pressure ratio raised to power gamma minus 1 by gamma. So that gives you T5S is 550.6. And similarly, in case of an expander or the turbine, it will be actual by ideal. So rearranging, this is what you get. So T5 will become 627.4 Kelvin. So doing an energy balance across the regenerator will give me m.2 H2 plus m.5 H5, which is the incoming fluid, equals m.3 H3 plus m.6 H6. So incoming is 2 and 5, and going out is 3 and 6. So that's what is given. Energy in equals energy out for the steady state. So since Cp is constant and mass flow across the cycle is constant, so both will get cancelled out. You get T2 minus T3 equals T6 minus T5, and what is given is T3 minus T3 and T5 has a 10 Kelvin temperature difference. So T3 is T5 minus T10. So T3 will come out to be 617.4 Kelvin. With that, we can find out the previous relation T6. So T6 will be 631 Kelvin. So now we can find out the actual mass flow rate of air which is going in. So because we know the total net work output, so net work output is divided by the specific work output. So net work is 106 divided by the work generated is Cp T4 minus T5 in the turbine minus Cp T2 minus T1, which is the work supplied in the compressor, specific work supplied in the compressor. So substituting the temperatures and Cp as 1, we get mass flow rate as 0.9241 kg per second. So for an ideal mass flow rate, if we compare, we get 106, and substituting the temperature, it is 0.455 kg per second. So what this basically says is that ideally to generate the same amount of work, you need only this much amount of air to supply. So this in ideal case, it's actually bringing down your turbine and compressor sizes. So further, the heat input rate for both actual and ideal cases can be found from the energy balance of the combustion chamber. So the heat input is again H4 minus H3. So it will come out to be 413.8 kilowatt, and ideally so your enthalpy difference will be same, but your mass flow rate will be lower. So ideally you would have given 203.8 kilowatt. So again, this requires that if you are using fuel, you will require a larger amount of fuel to provide this amount of heat. So the heat rejected is again m dot H6 minus H1. So substituting will be 307.4 kilowatt for the actual, and it's lower because lower mass flow rate will be 149.7 kilowatt. So next is we need to find out the entropy generated in the combustion chamber. So for that, if you do an entropy balance across the combustion chamber, so we'll get entropy generated is the stream going out minus stream coming in, entropy going out minus entropy in, minus heat added by the temperature, the source temperature here. So S4 is 6.376 kilojoule per kg Kelvin for this pressure and temperature, and S3 is 6.175 kilojoule per kg Kelvin for the same pressure and temperature. So substituting the values here, and your source temperature is 2500, so entropy generated will come out to be 0.02 kilowatt per Kelvin. So next is we need to find out the exergy destruction in the combustion chamber. So that is straight away you can find it out by T0 into delta S, or you can combine this entropy generated with the first law into T, the entropy generated in T0 added with your first law will give me this exergy equation, m dot ex3 plus qc1 minus T0 by Ts into m dot 4 ex4 and exergy destroyed. So substituting exergy 3 at 3 is 480, exergy at 4 is 115.8 kilojoule per kg. This exergy destroyed comes out to be 238 kilowatt. So you see the energy efficiency is network, thermal efficiency is network by your heat added. So heat added is 413.8 kilowatt, and network is 106, so it comes out to be 256 to 25.6%, and exergy efficiency is network by your actual maximum work which you can get. So if you use an Carnot cycle, so that's what it gives. So Q into 1 minus T0 by Ts, so it will come out to be 29.1%. So next is after seeing we have Brayton cycle, so next comes as standard cycles, which you have Otto cycle, diesel cycle, which we see it and use it regularly. So we the bikes, your cars, so you have a petrol engine and a diesel engine. So petrol engine is close to an Otto cycle, and a diesel engine, so a diesel cycle. So how this process is, you have again 4 process. So first is you have this so 4 strokes engines, you have this inlet, and then you have come. So initially you have a suction stroke, so that's what is given by PC to 5, so where the fluid comes in, and so the air and fluid mixture in a Otto cycle. So you have carburetor, you air comes in So it sprays fuel, and this fuel air mixture is then taken inside the engine. So that goes inside, and then once it reaches the bottom, so it's just a piston, so it goes from top to bottom, and you have some clearance. So it goes from top to bottom and bottom to top. So this is one cycle or one stroke. So two stroke. So per cycle you have two strokes. So so again there's a 4-stroke engine. So this is a 4-stroke engine, and there's a 2-stroke engine. So this, what we generally use is a 4-stroke engine. So in the first stroke, so that is where inlet comes in. After that you are compressing it. So now we are at 1 when it is at the bottom dead center. Then you are compressing it to 2. So once it reaches the top position, now at this constant volume you are igniting the fuel air mixture, and the heat is added, and then it goes down. So because of the energy generated, the fuel air mixture does work, and it pushes the piston down. So from 3 to 4 it goes back, and then once it reaches, it's again compressed, and at constant volume you are taking away the fuel air mixture leaves the engine. So this is how the engine works. So we have this 4 process. So first is a compression process, so 1 to 2. So again you consider it as to be a reversible adiabatic or a isentropic process. So 1 to 2, and 2 to 3 is a constant volume heat addition. Then 3 to 4 use your expansion, or that's the working stroke or the power stroke, where you get the power. So 3 to 4, and then 4 to 1 is your exhaust, where it is considered as a heat rejection. So this is denoted in the PV diagram, and then and the same is shown in a TS diagram. So the isentropic process and the constant volume lines for 2 to 3 and 4 to 1. So the efficiency of this Otto cycle is represented as efficiency 1 minus 1 by your power pressure ratio raised to power gamma minus 1. And similar for a diesel cycle. So the only change is, instead of the heat addition at constant volume, it is now occurring at constant pressure. So that is the only change. So you have two isentropic, one constant pressure heat addition and constant volume heat rejection. So that is a change in the diesel cycle. So the efficiency of diesel cycle is given like this. So 1 minus 1 by pressure ratio raised by gamma minus 1 into beta k. Beta is your cutoff volume by volume ratios. It's called volume ratio, and then gamma into beta minus 1. And then you have a dual cycle. So this is how a dual cycle looks. So here the inlet process or the heat addition process is in 2 stages. Once you do it in a constant volume, and then in a constant pressure. So in actual cases, this is what the engine closely resembles a dual cycle, where because the pistons are moving, so you can say it closely resembles the diesel cycle. So this is how the diesel cycle dual cycle efficiency is given. Again you have this alpha pressure ratio and beta. So to compare these 3 cycles, you have Otto, diesel and dual cycle. So if we have same compression ratio and heat rejection, so that heat rejection is fixed, and we have same compression ratio, so though 2 pressures are fixed. In that case, Otto is given by 1, 2, 3a, 4, 1. So that will have the maximum area under the curve. So that will have more work generated and more efficiency. The next comes the dual cycle. You see, you can go to higher temperature. and comes to 3b, and then next comes the dual, and last is for the same pressure, so it can go only to 2, and then you do a constant pressure to 3c. So that limits your maximum temperature which you can reach. So the last efficiency is the diesel cycle. So the same is shown in a TS diagram. But if you have same maximum pressure, in that case you will have diesel cycle which will have more efficiency. Then comes the dual cycle, and minimum will have been the Otto cycle, because you are limited by the maximum pressure or the temperature which you can achieve. So with that, we will see some problems on these cycles. So first is the cylinder conditions at the start of compression in a spark ignition engine. So if it's spark ignition engine, it's a petrol engine, or it all works in an Otto cycle. Operating on an air standard Otto cycle are 60 degrees Celsius and 98 kilopascal. The engine has a compression ratio of 9.5:1. So your compression ratio is 9.5, and uses a gasoline engine with air fuel ratio is 15.5. So that is mass of air by mass of fuel. The combustion efficiency is 96%, and it can be assumed that there is no exhaust residual. So you need to calculate temperature at all states in the cycle in degrees Celsius, and pressure at all states in the cycle in kilopascal, the specific work done during power stroke, and heat added during combustion, the net specific work done, and indicate the thermal efficiency. So first is T1, which is 60 degrees Celsius. So converting into Kelvin, it will get 333 Kelvin. So pressure, inlet pressure is 98 kilopascal. Since the compression process is isentropic, so we'll use an adiabatic expression. So T2 equals T1 raised to power pressure ratio raised to power gamma minus 1. So this is volume ratio, volume ratio raised to power gamma minus 1. So that will come out to be 732 Kelvin, and again P2 equals P1 into your compression ratio raised to power gamma. So 98 into 9.5 raised to power 1.35 comes out with 2047 kilopascal. So your heat addition is given as heat addition into your combustion efficiency equals air fuel ratio plus 1. So that gives you the total amount of mass presented. So inlet, the heat input is mass of fuel into your calorific value of fuel into combustion efficiency. So on the right side you will have the total mass into CV into delta T. So dividing by mass of fuel, you will get mass of air by mass of fuel plus mass of fuel by mass of fuel, which will be 1. So CV and T3 minus T2. So substituting, the only unknown is T3. So we will get T3 as 3506 degrees Celsius. So since the heat addition is at constant pressure, constant volume, so P3 is P2 into T3 by T2. Substituting the pressures and temperature, we will get 10.568 kilopascal. So again from there we can estimate temperature at 4, because it goes to an expansion, adiabatic expansion. T4 equals T3 is 1 by RC raised to power gamma minus 1. So substituting, we will get T4 as 1446.4 degrees Celsius and P4 as 506 kilopascal. The specific work done during power stroke is this is your adiabatic work done. So MRT specific work, so R T4 minus T3 by 1 minus gamma. So substituting, we get work done in the power stroke to be 1689 kilojoule per kg. Next is heat added during combustion. Heat added is CV delta T, So Q or CV T3 minus T2, or the other way is mass of fuel into Q into your combustion efficiency, but we don't know the mass of fuel. And we need in terms of air. So CV T3 minus T2 will give me 2502 kilojoule per kg. So the net specific work done will be again the work during compression which is done comes out to be 327 kilojoule per kg. So the net work done will be the power stroke work minus the compression work will give me 1362 kilojoule per kg. So that is the net work which is generated, and indicated thermal efficiency is nothing but the work done divided by the heat added. So 1362 divided by 2502 will come out to be 54.5%. And if we use the formula, so 1 minus 1 by RC, so RC we can write it in terms of temperatures. So T1 by T2 will give me 0.545, which is the same as what we got. CI engine, so a compression ignition engine. So here is a diesel cycle, so it's operating on the air standard diesel cycle, a cylinder condition at the start of compression of 65 degrees Celsius and 130 kilopascal. So light diesel fuel is used at an equivalence ratio of 0.8 with a combustion efficiency of 0.8. So compression ratio is 19 and stoichiometric air fuel ratio is 14.5. So for this we need to find out temperature, pressure, cutoff ratio, and indicate thermal efficiency, and heat lost in exhaust. Similar way, T1 is given, and T2 is again your adiabatic process. So T1 is RC raised to power gamma minus 1. So substituting the value, we get T2 as 947 Kelvin or 674 degrees Celsius, and P2 will be P1 into RC raised to power gamma. So 130 into 19 raised to power 1.35 comes out to be 6922 kilopascal. So the equivalence ratio is nothing but the air fuel ratio, stoichiometric air fuel ratio by air fuel ratio. So from this, the equivalence ratio is 0.8, and they say the stoichiometric air fuel ratio is 14.5. So this gives me air fuel ratio is 18.125. So again, using the same formula which we did, Q into combustion efficiency is a air fuel ratio plus 1 into CV into delta T. So again, substituting the values, the only unknown is T3. So T3 comes out to be 2913 Kelvin, which is 2640 degrees Celsius. So P3 equals P2, which comes out to be 6922 kilopascal, because it's a constant pressure process. Previously it was a constant volume. This is a diesel cycle, so it will be a constant pressure process. So V4 equals V1 so RT1 by P1, which so the volume comes out to be 0.7462 meter cube per kg. So V3 is RT3 P3. Substituting the values, by get V3 as 0.1208. So this will give me the cutoff ratio. So T4 is T3 into V3 by V4. Raised to power gamma minus 1. So that comes out to be 1267 degrees Celsius, and P4 is P3 into again V3 by V4 raised to power gamma. So since it's an adiabatic process, so T4 comes out to be 592 kilopascal, and beta cutoff ratio is T3 by T2, since that process constant pressure, T3 by T2. So V3 by V2 will be T3 by T2 for an ideal gas. So T3 by T2 will be 3.08. This is the since it's a constant pressure, so that will be my cutoff ratio. Next is to find out the indicated thermal efficiency. So using the formula, we can substitute the values. It comes out to 54.7%, or the other way around is to find out the net work and the heat added, and we can get the thermal efficiency. So next is to find out the heat lost in exhaust. So heat lost in exhaust is Cp T3 minus T2, or directly you can find Cp T4 minus T3 minus T4. Sorry, T4 minus T1. So heat added is comes out to be 2178, and the net work is 1191 kilojoule per kg. So heat rejected is will be Qin minus W, which is 987 kilojoule per kg. So that is a problem on diesel cycle. So moving on to next one, we have a compression ignition engine for a small truck is to operate on an air standard dual cycle with a compression ratio of RC equals 18. Due to structural limitation, maximum allowable pressure in the cycle will be 9000 kilopascal. Light diesel fuel is used at a fuel air ratio of, so instead of air fuel ratio, I have given fuel air ratio, so 0.054. The combustion efficiency can be considered 100%. Cylinder conditions at the start of compression are 50 degrees Celsius and 98 kilopascal. Calculate a maximum indicated thermal efficiency possible with these conditions. Peak cycle temperature under conditions of part A, and C, minimum indicated thermal efficiency possible with this condition, and D, peak cycle temperature under condition of part C. So we need to find out peak temperature and what is the maximum and minimum indicated thermal efficiency and the peak temperature for both the cases. So if you see this, how the cycle looks, 1, 2, 3 and 4, this will give you the maximum for the same compression ratio, compression ratio. This is what is possible. 1, 2, 3A, 4, which is given by the Otto cycle, but ஹலோ சொல்லு, என்னாச்சு? கிளாஸ் எடுத்துருக்கு, என்னாச்சு வீட்டில்? இல்லை, என்னாச்சு? அர்ஜென்ட்டா? வீட்டுக்கு வந்துட்டேன். சரி. So the maximum possible is given by an Otto cycle, but with the limitation that it cannot cross the maximum pressure of 9000 kilopascal. So after 2, when you are doing heat addition, it can at constant volume, so the pressure and temperature will rise, and it can go to a maximum of 9000 kilopascal. If that is the maximum it can go, 3A is 9000 kilopascal, then it will fully go into an Otto cycle. Else for the given heat addition, it will follow a dual cycle, so it can go to 9000 kilopascal, and then the rest of the heat addition will happen at constant pressure, and then it will follow a dual cycle. So that will give me the maximum indicated thermal efficiency. So this limitation pressure we have to see, heat addition, what maximum pressure can be reached, and then the minimum is again which we have already discussed, will be given by the diesel cycle for the same compression ratio. So the minimum is provided by the diesel cycle. So that's the maximum and minimum indicated thermal efficiency cycles. So the first we'll see the maximum one. So possible is when it is done, heat addition combustion is done at constant volume. So your temperature Tx, we'll see Tx is T2 into P3 by P2, since it's constant volume process. So P3 is known 9000 kilopascal, and we have found out P2 from assuming a reversible adiabatic process for 1 to 2 will come out to be 4851 kilopascal, and T2 is 615 degrees Celsius. Substituting the values, I get Tx as 1647 Kelvin. Similarly, the air fuel ratio will 18.52, and substituting in this expression, the total Q is mass of fuel into Q into combustion efficiency, equals mass of fuel plus mass of air into Cv into Tx minus T2 for constant volume heat addition, and then mass of fuel plus mass of air into Cp T3 minus Tx is the constant pressure heat addition in the dual cycle. So assuming combustion efficiency is 1 and dividing by mass of fuel, my heat addition calorific value is 42500, and substituting the rest of the values, I get T3. So T3 comes out to be 3050 Kelvin. So this shows that the heat addition is more and follows a dual cycle. If it would have been auto cycle, then T3 will come out to be same as 1647. So there will be no constant pressure heat addition. Since the heat provided is more, it will follow a dual cycle. So it will come till 9000 kilopascal, and then it will follow a constant pressure. So now the T3 is the maximum temperature, peak temperature is 3050 Kelvin. So with that, the pressure ratio is Px by P2. So Px by P2 is the pressure ratio. So that is 9000 divided by 4851, which is 1.855, and cutoff ratio is again T3 by T2, which is the constant volume, constant pressure heat addition. So the T3 by T2 will give me the cutoff ratio, which is 1.852. Substituting the dual cycle efficiency formula, it comes out to be 60.3%. So that is the maximum possible indicated thermal efficiency for this cycle, and the peak temperature is 2777 degrees Celsius. Similarly, the minimum thermal efficiency is when it is operated as a diesel cycle. So when it operates as a diesel cycle, the Q is again AF plus 1, and the whole heat addition is done as at a constant pressure. So Cp into T3 minus T2. So we know T2 is 888 Kelvin. So in that case, T3 will come out to be 2853 Kelvin. So the peak temperature is again 2580 degrees Celsius. So again for this, the cutoff ratio is T3 by T2. So this is 3.213. So substituting the thermal efficiency for the diesel cycle, what we get is 53.3%. So that is the efficiency for a dual cycle. Just a minute. With that, we have covered all the ascent cycles. So we have shown for each case the auto cycle, then comes your diesel cycle and dual cycle, which is a combination of auto and diesel cycle, and we So numeric on each of the cycles. Uh, so the variation is only in the process of heat addition. So the three other processes remain same. There is a reversible adiabatic or isentropic compression. Then your heat addition comes. So heat addition is constant volume for Otto and constant pressure for diesel, and a combination for both in dual. So you have constant volume and then constant pressure in a dual cycle, and then you have reversible adiabatic expansion and then constant volume heat rejection or exhaustion. So that's how R standard cycle looks, and we have seen how their efficiencies are related at what condition what is maximum. So we have seen that for a given compression ratio, the maximum is by Otto cycle and then minimum is by diesel cycle. So the dual is always lies between, and then if you have limited by the maximum pressure or the maximum temperature, then you have maximum by diesel and then minimum by Otto. So that's where the condition is. So with that we'll move on to vapor compression cycles. So this is the last part of the cycles. So we have here vapor compression cycle. So if you see, this is a refrigerant cycle. So it's a power consuming cycle. So previously which we saw, or all our aim was to get a work done. So we need power output to run something. So our main aim of the cycles was to produce power. This vapor compression cycle is a refrigeration cycle. So here our objective is to provide cooling and not the work. So here we give some work and that will provide some cooling, or in some cases as a heat pump we want heating to be provided. So that will change this thing, whether we need a heat to be provided or heat to be taken out. So heat taken out in a refrigerator. So if you see, the cycle is somewhat closely resembles your Rankine cycle. So where just that the process is reversed, the cycle is reversed. So here the turbine case is now replaced with the compressor, and cycle is going the other way around. So 1 to 2 you are having compression, and then 2 to 3 you are having heat rejection, so you are condensing it back. Then 3 to 4 ideally it should have been a constant entropy expansion, but since we talked multiple instances we saw of the two-phase cases in the turbines, which and how we want to avoid it, and then the compressor. So the same case is here, so which we don't want, and so we replace this constant entropy process with a isenthalpic process, which is a constant enthalpy process. So what this does is it replaces one of the component with an expansion valve. So if you do an energy balance across a valve, what we get is so Q minus W, and the energy in minus energy out. So Q minus W is energy in minus energy out. So Q is 0, W is 0, because expansion valve there is no heat addition and there is no work output. And energies, if you see, enthalpy in kinetic energy and then a potential energy. So kinetic and potential energies will be 0. So only is enthalpy in minus out is 0. So your enthalpies will be constant across a expansion valve. So you are putting an expansion valve. So what this does is you are getting rid of one moving component, so which increases the reliability of the system. So that's the advantage here, changing from an isentropic process to an isenthalpic process. So but you are losing some of the refrigeration because of that. So there is some exergy loss by doing a isenthalpic process, which is given by this area 3, 4, 4 dash and so on. so which will cause an exergy restriction, so which is putting more work, because now it's not constant entropy. So then we are doing 4 to 1, where the heat is taken out, so the heat addition. So what this does is this cools the whatever space which is required to be cooled. So this what is cooling is provided between 4 to 1. So this is a constant pressure process. So now you have an isentropic compression, a constant pressure heat rejection, and then an isenthalpic process, and then constant pressure heat addition. So this is how an vapor compression system works, and this is how the system looks. So we have a compressor, then to a condenser where heat is rejected, and then expansion valve, and then an evaporator, and back to the compressor. Ideally we want it to be in vapor form when it enters the compressor. So to give you an example, so this piece here is, we have, if you see in your rooms around, you have air conditioners, the split air conditioner. So this condenser and compressor will be outside the box which you are keeping it outside. So that is your condensing unit. So that's where the condenser is, and you want to reject it to the ambient, so keep it outside. And inside is we have a evaporator and the expansion valve. So that's how this thing. So we can relate it to this VCRS with your air conditioner. So condenser and evaporators are nothing but heat exchangers. So normally in a Carnot cycle you add compressors and turbines, also expanders in a Carnot cycle. So that we replaced with the heat exchanger in the Rankine cycle. So similar idea, we do it in a vapor compression system as well. So that's then introduction to an vapor compression cycle. So we'll see some numericals on this. So you have R134A, which enters the compressor of a vapor compression refrigerant cycle at 120 kilopascal as a saturated vapor, and leaves at 900 kilopascal and 75 degrees Celsius. So the refrigerant leaves the condenser as a saturated liquid. The rate of cooling provided by the system is 18,000 BTU British thermal unit by R. So determine the mass flow rate of R134A and the COP of the cycle. Determine the COP of the cycle if the expansion valve is replaced by an isentropic turbine. Do you recommend such a replacement for a refrigerant system? So determine the COP if the evaporator pressure is 160 kilopascal and other valve values remain the same. Determine the COP if the condenser pressure is 800 kilopascal and the other values remain the same. So what we are doing is, first we are changing the expansion valve to an isentropic turbine. So initially there is a VCRS cycle, then we are making 3 changes. One, we are replacing the valve by an isentropic turbine. So what that effect it's making, and whether it can be recommended. Second is we are increasing the evaporator pressure from 120 kilopascal to 160 kilopascal, and then third, we are reducing the condenser pressure from 900 kilopascal to 800 kilopascal. So your refrigerant is R134A. So we'll go with an R134A chart or a table. This is like a stream table for R134A. So initially your pressure at 1 and 4 is 120 kilopascal, and 2 and 3 is 900 kilopascal. So P1, ideally it's saturated vapor to the compressor inlet. So at this point my enthalpy is 236.97 kilojoule per kg, and we compress it isentropically. We reach 2S, but your exit temperature to the compressor is given, which is 900 kilopascal and 75 degrees Celsius. So enthalpy is there at this point is 310.51 kilojoule per kg, and P3 stage 3 is your saturated liquid condition for ideal case. So for this and 900 kilopascal, my enthalpy is 101.61 kilojoule per kg, and for an isenthalpic process, the H3 and H4 will remain same. So now we know all the enthalpies. So now we can calculate the specific work input and the specific heat which is getting added, or the specific cooling which is provided. So W is H2 minus H1, which comes out to be 310 minus 0.51 minus 236.97 is 73.54 kilojoule per kg, and the heat which is taken out in the evaporator will be 135.4 kilojoule per kg. So here COP is nothing but just like efficiency, but efficiency cannot be greater than 100% or greater than 0 to 1. COP is can be greater than 1, so that's why you call it as coefficient of performance instead of efficiency. So COP is nothing but your cooling capacity, which is the heat which is taken by the evaporator divided by the work which you are providing. So that we need to find out the first initially the mass flow rate of the refrigerant, which is the total cooling load which is required, which is 18,000 British thermal unit, which is 1 kilowatt is 3,412.14 British thermal unit. So, or you can say straight away 5.275 kilowatt. I think I'll make change in the problem. 5.275 kilowatt is the cooling load, and the specific cooling load is 135.4 kilojoule per kg. So that gives me 0.039 kg per second of mass flow rate of the refrigerant. So the COP of the refrigerator will be your cooling load, specific cooling load divided by specific work. So that comes out to be 1.84. So that is the COP. Now the first case is where you are replacing the valve with an isentropic turbine. So your P3 is 900 kilopascal and X3 is 0. So initially, so at that point your entropy is 0.3738. So now instead of enthalpy being constant, you are taking entropy to be constant. So when we do that, you are at state 4 for pressure of 120 kilopascal and entropy of 0.3738. You lie in a two-phase region, and the enthalpy at there comes out to be 92.98. So for this you need to find out if can get it straight away from the chart, or you have to find it find the dryness fraction and then calculate the enthalpy. So in this case the turbine output will be 8.63 kilojoule per kg, and the compressor net work which is provided is now it is reduced by 8.63, so comes out to be 64.91 kilojoule per kg, and your QL, which is the heat load in the evaporator, has gone up because H4S is lower. So H1 minus H4S will come out to be 144 kilojoule per kg. So for this case the COP is now 144 by 64.91, which is 2.21. So the COP has increased by 20.1% by replacing with a turbine. So this makes thermodynamic sense, but actually it's not possible. As discussed previously, so you encounter two-phase and it can damage your system, turbine and this thing, so and it's not reliable. So this all causes it to not be used practically, but it makes thermodynamic sense, but it cannot be used practically. So next is, in the evaporator pressure is 160 kilopascal instead of 120 kilopascal. So in that case your whole of H4 and H1 will change to 1, but your COP value, so H2 and H1 values will change. So finding out the new H2 and H1 value, so H1 will be 241.12 and H2 will be 310.51. So with that your COP now becomes 2.01. So if you see, this has increased your COP, but it comes at the cost that your evaporating temperature has increased from minus 22.3 to minus 15.6 degrees Celsius. So what this is that your performance has increased, but if your cooling requirement is at lower temperature, then this is not possible. But if your cooling requirement is greater than minus 15, then this makes a more efficient system. Then if the condenser pressure is 800 kilopascal, so you are reducing from 900 kilopascal to 800 kilopascal. So in this case, both H2 and H4 will vary. So finding out H2 and H4, 311.92 and H4 is 95.47. So substituting, this COP is 1.89. So if you see, your again here COP has increased a little by 2.7%, but this has reduced your condensing temperature to 35 from 35.5 to 31.3. So next is a similar problem with R134A, but now it's an heat pump. So we need to find out dryness fraction of the refrigerant entering the evaporator, the discharge temperature assuming the specific heat of vapor as 0.996 kJ per kg Kelvin. So it is operating between 15 and 50 degrees Celsius. So and the heat required is 100 megajoule per hour. And also we need to find out the piston displacement of the compressor. The displacement is too much. So and COP, the specific volume is given for saturated vapor is 0.04185 meter cube per kg. So this is the values given at 15 and 50 degrees Celsius. So the pressures are given mega Newton per meter square. The enthalpies are given for saturated liquid and saturated vapor, and similarly for entropy. So the dryness fraction of refrigerant entering the evaporator will be, so it will be equal to H4 will be equal to H3. So that is your saturated liquid at 50 degrees Celsius, which is 271.62. So H3 minus HF at 15 degrees Celsius divided by your G minus HF. So this is 417.1 minus 220.48 gives you 27.4% is the dryness fraction. And similarly discharge temperature, so your entropy is constant, so S1 equals S2 and S2 can be written as S2 dash plus Cp ln T2 by T2 dash. So S2 dash is your entropy for saturated vapor at 50 degrees Celsius, and then there is superheating, so that's what is written. So in that case, from here we can find out T2. So T2 comes out to be 327.15 Kelvin. So similarly, enthalpy at discharge will be H2 is H2 dash plus Cp T2 minus T2 dash. Substituting. So because you are heating, so at this point saturated vapor, then you are superheating, superheated point to find out 2. So a enthalpy at your saturated vapor plus this enthalpy difference for superheating, which is vapor, Cp delta T. So this comes out to be 427.2 kJ per kg. So mass flow rate of refrigerant is again heat load divided by the specific enthalpy difference for cooling. So this is given as 100 megajoule per hour. So 100 into 10 power 6. So since we are writing enthalpy in kilojoules, so in 100 into 10 power 3 kilojoule divided by 3600 divided by your enthalpy difference between H4 minus, since this is heat pump, so you have to take it at the top condenser, so H2 minus H3, so that is your heat pump application. So this is your load. So 427.2 minus 271.62 gives you 0.179 kg per second. So this is the mass flow rate. So if you multiply with the specific volume, you will get the piston displacement volume. So next is power consumption. So power consumption W is mass into H2 minus H1, which comes out to 3.6 kilowatt. You can convert it to horsepower divided by 746. And heating capacity is m dot into H2 minus H3, so which comes out to be 27.9 kilowatt. So COP now is for heat pump will be the condenser enthalpy change divided by the work specific work in compressor, so it comes out to be 7.75. So see, this is the last problem for today on VCRS. So we have a refrigerator using R134A. It's a refrigerant used to keep a space at minus 10 degrees Celsius by rejecting heat by ambient air at 22 degrees Celsius. So R134A enters the compressor at 140 kilopascal at a flow rate of 375 liters per minute as saturated vapor. The isentropic efficiency of the compressor is 80%. So the refrigerant leaves the condenser at 46.3 degrees Celsius as a saturated liquid. Determine the rate of cooling provided by the system, the COP, the exergy destruction in each component of the cycle, second law efficiency of the cycle, the total exergy destruction in the cycle. So we have a refrigerator. So what is given is it is operating between minus 10 and 46.3 degrees Celsius. Your ambient temperature is 22 degrees Celsius, and they say your evaporator is at 140 kilopascal and your room is at minus 10, and the flow rate is 375 liters per minute. Compressor efficiency is 80%. So see how to solve this. So for finding out mass flow rate, so mass flow rate is m dot by m dot is your volume flow rate divided by specific volume. So volume flow rate is given as 375 liters per minute. So converting into meter cube per second, it will be 0.375. So 1 liter is 10 power minus 3 meter cube. So 0.375 divided by 60 gives me meter cube per second, divided by the specific volume. The specific volume at 1 for 140 kilopascal is 0.1402. So it will give me mass flow rate of 0.04458 meter kg per second. So next is the refrigerant load, which is the rate of heat rejected, and the power input are. So refrigeration m dot H1 minus H4. So that will be at 46.3 degrees Celsius, and saturated liquid, that enthalpy is 117.77, and H1 is your saturated vapor at 140 kilopascal, so that is 239.17. So into mass flow rate gives me 5.41 kilowatt, and similarly the heat added m dot H2 minus H3. So to find out H3 and H2, can find out from H1, assuming an isentropic process, we find out H2s, and using your compressor efficiency of 80%, we can find out H2. So H2 comes out to be 295.32. So heat addition is in condenser is 7.92 kilowatt, and the work done is 2.5 kilowatt. That is just QL minus QH. So the COP of the cycle will be QL by work done, which comes out to be 2.16. Since the ambient is at 22 degrees Celsius, so 273 plus 22 is 295 Kelvin. So we need to find out the exergy destruction in each of the component. So for compressor, this is m dot S2 minus S1. So that comes out to be 0.001502 kilowatt per Kelvin. So exergy destruction will be T naught into delta S, so which is 0.4432 kilowatt. And in the condenser, PS generated is m dot S3 minus S2 out minus in plus heat rejected by TH. Since it is rejected to ambient, so ambient is receiving heat, so hence positive. So plus QH by TH. So substituting the values, I get exergy destroyed 0.6508, so 6308 kilowatt. For the expansion valve, similarly your entropy generated is m dot S4 minus S3, comes out to be 0.001916 kilowatt per Kelvin, and exergy destroyed will be 0.5651 kilowatt. And for the evaporator, similar to what we did in condenser, but so m dot S1 minus S4 out minus in plus QL by TL. So your, since the room is at minus 10 degrees Celsius, so your temperature source is 263 and QL is 5.41. Substituting, you get exergy destroyed as 0.2054 kilowatt. So the exergy of the heat transfer from the low temperature medium is what we get. So for the if you are using the same heat, you are getting QL T naught by TL minus 1. So it is 0.6585 kilowatt. This is also the minimum power input for the cycle. So the second law efficiency of the cycle is 0.6585 divided by 2.503. So the exergy efficiency will be 26.3%. Or we can straight away write 1 minus summation of exergy destroyed divided by the work done. So that will also give us the same formula, same value. And or else we can use COP divided by COP of Carnot. So COP of Carnot will be TL by TH minus TL, where TL is minus 10 and TH is 22. So substituting, we get COP of Carnot is 8.22. So substituting, your actual COP of the cycle is 2.16. So 2.16 divided by COP of Carnot, which is 8.22. So it becomes again 0.263 or 26.3%. So it will be giving the same exergy efficiency form value. What this is it is close to 1/4 as efficient as the Carnot. So with that we have finished the cycles. So today we saw a variety of cycles. So we start with Brayton, then we saw ash and cycles, and then with the refrigeration cycle, the vapor compression cycle. So each are just a variation of the others. So with that we have finished the vapor compression system, and the other cycles. So next week we'll be looking at the psychrometric uh, processes, the psychrometric chart, and how we calculate air, because air is a mixture of both moisture and your gases. So how do we calculate each of it? How do we, what is the temperatures, and how we calculate humidity and so on, and how it is represented in a chart. So that all will be seen in the next week. So we'll be covering that in the next week. So this ends the cycles portion. So with that I'll end my session for today. Thank you.